Hello, and welcome. I'm your night librarian. So glad you're here tonight. I hope you don't mind. I've put on some relaxing music for you. It should begin shortly, softly in the background. Let's take a moment to slow down together. There's nothing you need to do, and nowhere you need to be. Let's light up the candle. Just a small, warm glow, steady and comforting. Take a gentle breath in and let it go. Tonight, we'll be talking about something simple, something calm, something that you can drift in and out of as you rest. You don't need to stay awake. Just listen, relax, and allow yourself to fall asleep whenever you're ready. Tonight, we begin our restricted section of the archives, a multi-volume catalog of our home galaxy. We start at the heartbeat of it all, the Galactic Core. In this volume, we explore the supermassive black hole Sagittarius A, the dense clusters of ancient stars, and the violent yet beautiful physics that holds the Milky Way together. We turn our attention inward, not to the sprawling spiral arms where our own sun makes its patient orbit, but to the ancient heart of our galaxy, to that dense, luminous core where stars crowd together like grains of sand in an hourglass. To the great central bulge. Let us begin. The great central bulge is older than almost anything you can imagine in our galaxy. When the Milky Way was young, a mere infant in cosmic terms, perhaps 2 billion years old, the bulge was already forming. Stars were being born in tremendous numbers, in great rushing waves of creation. They came into being so quickly, so furiously, that the process consumed nearly all the available gas and dust in that central region within just a few billion years. These are ancient stars, you see, old, patient stars, population 2 stars, as astronomers call them. They are metal poor, meaning they were born before generations of stars had lived and died and scattered heavier elements across the cosmos. They are the elders, the witnesses to our galaxy's youth. If you could somehow stand at the edge of the bulge and look upon it with your own eyes, protected, of course, from the radiation and the gravitational forces that would otherwise tear you apart, you would see something remarkable. You would see a warm, golden glow, not the fierce blue-white of young stars, but a softer, older light, the light of red giants and orange dwarfs, of stars in their long, slow autumn. The bulge is approximately 10,000 light-years in diameter. 10,000 light-years. To put that in perspective, dear listener, a single light-year is nearly 6 trillion miles. The distance light travels in 1 year, moving at 186,000 miles every second. And the bulge spans 10,000 of these immense distances across its width. Within this region, there are somewhere between 10 and 15 billion stars. Imagine that. 10 billion individual suns, each with its own nuclear furnace, each pouring light into the crowded darkness. They are packed so densely in some regions that if you lived on a planet near the bulge center, your night sky would never truly be dark. Thousands of stars would be bright enough to cast shadows. Your sky would glow with a perpetual golden twilight. Now, the shape of the bulge. This is where things become particularly interesting. For many years, astronomers believed it was simply spherical, a round ball of stars at the galaxy's center. But careful observations, particularly from infrared telescopes that can peer through the dust that obscures our view, revealed something unexpected. The bulge is not round. It is elongated, bar-shaped. In fact, our galaxy, you see, is what we call a barred spiral galaxy. At its heart lies not a sphere but a bar, a rectangular structure made of stars, perhaps 27,000 light years long, rotating slowly through the galactic center. This bar funnels gas from the outer regions toward the center, feeding the supermassive black hole that lurks there, enabling bursts of star formation. But there's more. When viewed from certain angles, the bulge appears to have a peanut shape, or perhaps an X shape, or a box shape, depending on your perspective. This peculiar geometry arises from the complex orbital motions of billions of stars, all responding to the gravitational pull of the bar, all weaving intricate paths through space and time. The stars in the bulge move differently than stars in the disk of the galaxy. In the disk, where our sun resides, stars orbit in relatively orderly, circular paths, like horses on a cosmic carousel. But in the bulge, orbits are chaotic, eccentric, tilted at wild angles. Stars plunge toward the center and then swing back out. They cross and recross each other's paths in a gravitational dance that has continued for over 12 billion years. And yet, somehow, collisions are vanishingly rare. Space, even in the densest part of our galaxy, is still mostly empty. The distances between stars, even in the bulge, are so vast that a star could orbit for the entire age of the universe and never come close to striking another. Still, the gravitational influences are profound. Stars in the bulge experience frequent close encounters, passing within a light year or two of one another. These encounters tug at their orbits, gradually reshaping them over millions and billions of years. The bulge is a place of constant, subtle transformation. Now, let us consider the metallicity of these stars. I mentioned that they are metal poor, but this requires some clarification. Astronomers use the word metal in a peculiar way. To them, anything heavier than hydrogen and helium is a metal. Carbon, oxygen, iron, silicon, all metals, in the astronomical sense. The oldest stars in the bulge have very few of these heavier elements because they were born from the primordial material of the early universe, which was almost entirely hydrogen and helium. But not all bulge stars are the same age. Some are younger, born from gas enriched by the deaths of earlier generations. These younger stars have higher metallicities. By studying the chemical composition of bulge stars, astronomers can piece together the history of star formation in the galactic center. They can see when great bursts of star birth occurred, when the rate slowed, when fresh gas was funneled inward by the bar. The bulge is a library unto itself. Its stars like pages in a book written over billions of years. There is something deeply humbling about the bulge, I think. Something that reminds us of our place in the universe. Our sun is a relatively young star, only about 4.6 billion years old. It orbits out in the disk, some 26,000 light-years from the galactic center, in a relatively quiet, orderly region. But the stars of the bulge, they are ancient. They have been shining since before our sun was born, since before the Earth existed, since before any planet in our solar system had even begun to form. If any of those stars host planets, and we suspect some do, those worlds would be unimaginably old. What might have arisen on such planets, given billions upon billions of years? It is a question that hangs in the air like incense in a cathedral. The great central bulge is also a place of tremendous energy. Not just the light of 10 billion stars, but other forms of energy as well. X-rays stream from the center, produced by matter falling toward the supermassive black hole, heating to millions of degrees as it spirals inward. Gamma rays flicker in mysterious bursts. Cosmic rays, particles accelerated to nearly the speed of light, pour outward from the core. If you could see the bulge in X-ray light, it would appear as a blazing, seething cauldron. In radio waves, you would detect vast magnetic fields, twisted and wound up by the rotation of the bar. In infrared, you would see the warm glow of old stars and the dust clouds that drift between them. Every wavelength of light tells a different story. Every form of radiation reveals another layer of the bulge's nature. And yet, for all its violence, for all its energy and chaos, the bulge is also a place of stability. It has existed for over 12 billion years. It will exist for billions more. The stars that compose it have long since settled into their wild but stable orbits. The bar rotates majestically, completing one revolution every few 100 million years. There's a rhythm to it, a pattern, an order beneath the apparent chaos. This is one of the great lessons of astronomy, I think, that the universe, for all its vastness and violence, follows rules. That chaos and order are not opposites but partners in an eternal dance. Before we close this record, let me share one more detail. One more small wonder. Deep within the bulge, there are structures called globular clusters. These are dense, spherical collections of stars, anywhere from 10,000 to 1,000,000 stars packed into a region only a few dozen light years across. They orbit through and around the bulge like satellites, some of them even older than the bulge itself. These clusters are time capsules. They contain some of the oldest stars in the entire universe, born less than 1 billion years after the Big Bang. Studying them is like reading the opening chapters of cosmic history. And there they are, swirling through the bulge, ancient and patient and enduring. Record 7. The Galactic Bulge. The galactic bulge is a dense, peanut-shaped heart of stars at the center of our Milky Way galaxy. It contains between 10 and 15 billion ancient stars, most over 10 billion years old, packed into a region approximately 10,000 light-years across. The bulge is part of a bar-shaped structure that rotates through the galactic center, its stars following chaotic, eccentric orbits that have remained stable for over 12 billion years. It glows with a warm, golden light, the light of old stars in their long autumn. Librarians note, imagine a swarm of 10 billion bees, each one a sun, glowing in a golden hue. They weave and dance in the darkness, never quite touching, their paths chaotic yet somehow harmonious. They have been dancing since before our world was born, and they will dance long after it is gone. This is the bulge, ancient, patient, eternal. Rest now, dear traveler. Let the golden light of 10 billion suns carry you gently into sleep. Sagittarius A, the gravitational anchor. There, in the constellation we call Sagittarius, the archer, hidden behind veils of dust so thick that visible light cannot penetrate, there lies the anchor, the linchpin, the silent sovereign around which 400 billion stars revolve. Sagittarius A star. The asterisk is intentional. You see, astronomers added it to denote that this object is unique, exciting, extraordinary, and it is all of those things. Let us begin with what it is. Sagittarius A asterisk is a supermassive black hole. Not simply a black hole, those stellar mass graves created when massive stars collapse, but something far more immense. It contains the mass of approximately 4 million suns. 4 million. Compressed into a region smaller than the orbit of Mercury around our Sun. Think about that for a moment. Our Sun, which contains 99.8% of all the mass in our solar system, which could fit over 1 million Earths inside its volume. Sagittarius A asterisk is 4 million times more massive, and yet, the event horizon, the boundary beyond which nothing can escape, is only about 12 million miles across. Tiny, by astronomical standards. You could fit it comfortably inside the orbit of Mercury. This is the paradox of black holes. Immense mass, incomprehensible density, and yet, vanishingly small. For decades, Sagittarius A asterisk was only a rumor, a whisper, a mathematical ghost. In the 1970s, astronomers detected a powerful radio source coming from the direction of the galactic center. They named it Sagittarius A, for the constellation and the fact that it appeared to be a discrete source of radiation. But the technology of the time was not sufficient to resolve fine details. They could tell something was there, something bright in radio waves, but not what it was. As the years passed and telescopes improved, That radio source was found to have structure. There were filaments, clouds, arcs of emission, and at the very center, a compact, bright point. This point was designated Sagittarius A asterisk, Sagittarius A star, the heart within the heart. But radio waves alone could not tell the full story. To truly understand what Sagittarius A asterisk was, astronomers needed to see how it affected the stars around it. And so began one of the most patient, meticulous observation campaigns in the history of astronomy. Starting in the 1990s, two teams of astronomers, one led by Andrea Ghez-Uckler and another by Reinhard Genzel of the Max Planck Institute, began monitoring individual stars in the immediate vicinity of Sagittarius A star. Using adaptive optics and infrared telescopes that could peer through the obscuring dust, they tracked these stars year after year, measuring their positions with exquisite precision. What they discovered was extraordinary. The stars were moving, not slowly, drifting lazily through space as stars in our neighborhood do, but fast, incredibly fast. Some of the closest stars were whipping around an invisible point at speeds exceeding 5,000 kilometers per second. That is nearly 2% the speed of light. One star in particular captured the astronomers' attention. It was designated S2, or sometimes S0-2, a bright, blue star, young and massive, orbiting something unseen. Over 16 years, from 1992 to 2008, astronomers watched S2 complete one full orbit. They mapped its elliptical path with extraordinary precision. At its closest approach to Sagittarius A asterisk, a point called periastron, S2 came within just 120 astronomical units of the invisible center. That is only 120 times the distance from the Earth to the Sun. In cosmic terms, it was skimming the surface of the abyss. And at that closest point, S2 was moving at nearly 5,000 kilometers per second. So fast that relativistic effects became noticeable. Time dilation, gravitational redshift, the very fabric of space-time warping around it. By carefully measuring S2's orbit and the orbits of dozens of other stars in that central region, astronomers could calculate the mass of the object they were orbiting. The numbers were unambiguous. 4 million solar masses, concentrated in a region no larger than our solar system. There was only one possible explanation: a supermassive black hole. But seeing the effects of the black hole was not the same as seeing the black hole itself. For that, astronomers would need to do something that seemed impossible. They would need to image the event horizon. Black holes, by their very nature, emit no light. The event horizon is the point of no return, the boundary where the escape velocity exceeds the speed of light. Anything that crosses that threshold is lost forever, vanished from the observable universe. Light itself cannot escape. So how do you photograph something that is, by definition, invisible? The answer lies in the material around the black hole. As gas and dust spiral inward towards Sagittarius A, they form what is called an accretion disk. This material heats up due to friction and gravitational compression, reaching temperatures of millions of degrees. At such temperatures, it glows brilliantly in X-rays and radio waves, and as it swirls around the event horizon, it creates a bright ring of emission, a halo of light surrounding the darkness. If you could image that ring with sufficient resolution, you could see the shadow of the black hole, the dark circle at the center where no light can escape. In 2017, a global collaboration called the Event Horizon Telescope, a network of radio telescopes spread across the Earth, working together as a single virtual telescope the size of the planet, turned their collective gaze towards Sagittarius A. For several nights, they gathered data, petabytes of it, so much information that it had to be physically shipped on hard drives because it was faster than transmitting it over the internet. Teams of scientists spent years processing the data, calibrating the instruments, correcting for atmospheric distortions and the rotation of the Earth. And then, on May 12, 2022, they revealed what they had found. An image, a photograph of Sagittarius A. It appeared as a bright, fuzzy ring of orange and yellow light, with a dark center. The ring was not perfectly circular. It was lumpy, turbulent, changing on timescales of minutes as hot plasma swirled around the event horizon. But the dark center was clear, unmistakable, the shadow of the black hole. For the first time in history, humanity had gazed directly upon the event horizon of a supermassive black hole. Not an artist's rendering, not a simulation, but an actual image. Photons that had traveled 26,000 years from the galactic center, captured by radio dishes and transformed into pixels. It was a moment of profound significance, a triumph of human ingenuity, patience, and collaboration. But let us return to the nature of the object itself, to the thing that lurks at the center of that image. Sagittarius A is surprisingly quiet, given its mass. Many supermassive black holes at the centers of galaxies are actively feeding, consuming vast amounts of gas and dust, shining brilliantly as quasars or active galactic nuclei. They can outshine entire galaxies, blasting jets of particles and radiation millions of light years into space. But Sagittarius A, it is subdued, dormant, almost. Oh, it feeds, but only a trickle. Occasionally, a clump of gas or an unlucky star wanders too close and is torn apart, producing a brief flare of X-rays or radio waves. But most of the time, Sagittarius A sits quietly, invisibly, holding the galaxy together with nothing but gravity. Astronomers estimate that it is accreting matter at a rate of only about 1,000th of a solar mass per year. A pittance. If it were feeding more actively, the galactic center would be far brighter, far more violent. Perhaps Sagittarius A has simply exhausted most of the available fuel in its immediate surroundings. Perhaps the chaotic orbits of stars and gas in the bulge prevent material from settling into a stable accretion disk. Or perhaps it is merely sleeping and will awaken in some distant epoch when a fresh supply of matter arrives. There is something almost patient about it, something ancient and watchful. Sagittarius A has been there for billions of years. It may have formed shortly after the Milky Way itself, growing from the merger of smaller black holes and the accretion of primordial gas clouds. Or it may have started as a seed, a black hole of merely thousands or tens of thousands of solar masses, and grown slowly over cosmic time. We do not yet know the full story of how supermassive black holes form. It is one of the great mysteries of astrophysics, but we know they are ancient, witnesses to the youth of the universe. And Sagittarius A has been sitting at the center of our galaxy, holding it together, shaping its structure and evolution, for longer than our sun has existed. Now, let us consider what it means to orbit such an object. The stars nearest to Sagittarius A exist in an environment unlike anywhere else in our galaxy. They circle the black hole in a region called the S cluster, a dense collection of bright, massive stars packed into a space smaller than our solar system. These are not ordinary stars. Most of them are young, only a few million years old, which presents an immediate puzzle. Young, massive stars should not exist so close to a supermassive black hole. The tidal forces, the intense radiation, the chaotic gravitational environment, all of it should make star formation impossible in that region. And yet, there they are. One hypothesis is that these stars did not form where they are now. Perhaps they were born farther out, in a more benign environment, and then migrated inward. Or perhaps they formed from the disk of material around the black hole itself, in a brief period of intense accretion when conditions were, paradoxically, just right for star formation. We do not know for certain. The S-cluster stars remain an enigma wrapped in fire and gravity. But what we do know is how they move. Take S2, that star we mentioned earlier. Its orbit is a stretched ellipse, bringing it as close as 17 light-hours from the event horizon at Periastron, then swinging it back out to a distance of about 1,500 light-hours at aphelion. One complete orbit takes 16.05 years. During its closest approach in 2018, astronomers watched with every instrument they could bring to bear. They measured the star's velocity with incredible precision. They watched for the subtle shifts in its light caused by gravitational redshift, the way photons climbing out of the black hole's deep gravitational well lose energy and stretch toward the red end of the spectrum. And they saw exactly what Einstein's theory of general relativity predicted. The star's light was redshifted by about 200 kilometers per second worth of velocity. Space around the black hole was so severely curved that photons had to work to expend energy just to escape. And S2's orbit did not close perfectly. It precessed, rotating slowly around the black hole, tracing a rosette pattern over many orbits. These were not effects predicted by Newton's law of gravity. They could only be explained by relativity, by the warping of space-time itself. Sagittarius A became a laboratory for testing our understanding of gravity under the most extreme conditions accessible to observation. But there are stars that venture even closer than S2. In 2020, astronomers detected a faint object designated S4714. This star, or perhaps it is a compact stellar remnant, has an orbit that brings it within just 12.6 astronomical units of Sagittarius A at periastron. That is closer than Saturn orbits our Sun. At that distance, it reaches speeds of nearly 8% the speed of light, 30,000 kilometers per second. So fast that time dilation becomes significant. A clock on S4714 would run noticeably slower than a clock farther from the black hole. If you could somehow stand on such a world, assuming it had not been torn apart by tidal forces, you would experience time differently than we do here on Earth. Your seconds would stretch, your minutes would lengthen, and when you looked out at the black hole, you would see the event horizon looming impossibly close, a perfect circle of darkness surrounded by a maelstrom of hot, glowing gas. The stars themselves would appear distorted, their light bent by the intense gravitational field. Multiple images might appear, light from a single star taking different curved paths around the black hole to reach your eyes. Space itself would be twisted, torn, reshaped into something almost unrecognizable. And yet, somehow, these stars survive. Year after year, orbit after orbit, they plunge toward the abyss and swing back out again. They endure. There is something almost defiant about them, something beautiful in their dance with oblivion. Now, let us turn our attention to the event horizon itself, to the boundary of the black hole. For Sagittarius A, the event horizon, also called the Schwarzschild radius, has a diameter of about 24 million kilometers, roughly 17 times the diameter of our Sun. If you could somehow replace our Sun with Sagittarius A, the event horizon would fit comfortably inside the orbit of Mercury. At the event horizon, the escape velocity equals the speed of light. This is the point of no return. Cross this threshold, and no force in the universe can bring you back. Not rocket engines, not nuclear explosions, not anything. You would fall inexorably inward, toward the singularity at the center. What is the singularity? According to general relativity, it is a point of infinite density, a place where the curvature of space-time becomes infinite, where all the mass of the black hole is compressed into zero volume. It is a place where our equations break down, where physics as we understand it ceases to make sense. But we do not truly know what lies at the center of a black hole. The singularity is hidden behind the event horizon, what physicists call cosmic censorship. The universe, it seems, does not allow us to see such extremes directly. We can only infer, calculate, speculate. Perhaps quantum gravity, the yet undiscovered theory that would unite general relativity and quantum mechanics, will reveal something different at the center, not a singularity, but some other exotic structure, a remnant, a bridge to another universe, a frozen moment where time itself ceases. We do not know, and that is both frustrating and wonderful. If you were to fall towards Sagittarius A asterisk, what would you experience? First, assuming you began your fall from a safe distance, you would accelerate slowly at first, then faster and faster as you approached. The black hole would grow in your vision, not as an object, but as an absence, a circular region of perfect blackness surrounded by a bright ring of light, the photon sphere, where light orbits the black hole in unstable circular paths. Behind that ring, you would see the distorted, compressed image of the entire universe. Stars and galaxies, their light bent around the black hole, squeezed into a shrinking circle of sky. As you fell closer, tidal forces would begin to make themselves known. The gravitational pull on the parts of your body nearest the black hole would be stronger than the pull on the parts farther away. You would be stretched. Astronomers call this spaghettification. For a supermassive black hole like Sagittarius A asterisk, the tidal forces at the event horizon are relatively gentle. You might actually survive crossing it, at least for a moment. The stretching would become unbearable only as you fell deeper inside. But here's the strange thing. As you fell, you would notice nothing unusual about your own experience of time. Your watch would tick normally. Your heartbeat would be steady. From your perspective, you would cross the event horizon in a finite amount of time and continue falling inward. But to an observer watching from a safe distance, something very different would happen. They would see you slow down as you approach the event horizon. Your movements would become sluggish. Your light would redshift, shifting toward longer and longer wavelengths. You would grow dimmer, redder, until finally you would fade from view entirely, frozen at the edge of the event horizon, asymptotically approaching but never quite crossing. This is the paradox of black holes. Two different but equally valid perspectives on the same event. Time itself behaves strangely near a black hole. The closer you get to the event horizon, the slower time flows relative to distant observers. This is not an illusion. It is a real effect, measurable and confirmed by countless experiments. Gravity slows time. Near Sagittarius A asterisk, time is running measurably slower than it is here on Earth. Not by much. We are 26,000 light years away, after all, but by a tiny, detectable amount. And for the stars in the S cluster, skimming close to the event horizon, the effect is profound. They are aging more slowly than stars farther out. Not by much, only by fractions of percent, but enough to measure. The black hole is not only an anchor in space, but an anchor in time. Sagittarius A asterisk also affects the space around it in other ways. Its immense gravity creates what we call gravitational lensing. Light from stars behind the black hole is bent as it passes nearby, creating distorted, magnified images. In some cases, a single star can produce multiple images. It's like taking different curved paths around the black hole. In extreme cases, if a star were to pass almost directly behind Sagittarius A asterisk, its light would be smeared into a ring, an Einstein ring, named for the physicist who first predicted the effect. These lensing events happen rarely, but when they do, they provide another tool for measuring the black hole's mass and spin. Spin. Yes, Sagittarius A asterisk is rotating. Like all black holes, it possesses angular momentum. It spins. We do not yet know exactly how fast it is spinning. Estimates suggest somewhere between slowly and moderately fast, but the rotation has profound effects. A spinning black hole drags space-time around it in a phenomenon called frame dragging. Near the event horizon, space itself is pulled along with the black hole's rotation, like water swirling down a drain. This creates a region called the ergosphere, where it is impossible to remain stationary. You would be forced to rotate with a black hole, whether you wanted to or not. There is so much we still do not understand about Sagittarius A star. So many questions remain. How did it form? How fast is it truly spinning? What will happen to it in the far future, when the universe has aged for trillions upon trillions of years? One day, Sagittarius A asterisk might consume more material, flaring to life as an active galactic nucleus. Or it might remain quiet, growing imperceptibly slowly over the eons. Eventually, far, far in the future, it might begin to evaporate, losing mass through a quantum process called Hawking radiation. But that is so far ahead that it is almost meaningless to contemplate. The timescale for a black hole of this mass to evaporate is 10 to the power of 100 years. A Google years. By then, all the stars will have burned out, all the galaxies will have dispersed, and the universe will be cold, dark, and nearly empty. Sagittarius A asterisk will be among the last objects to disappear. For now, it sits at the center of our galaxy, patient, invisible, known only by the way it makes the stars around it dance. It is the anchor, the keystone, the silent heart, and we orbit it, all of us, every star and planet and moon in the Milky Way, held in its gravitational embrace. Let us consider, for a moment, what it means that this object exists at all. A black hole with a mass of 4 million suns. How does such a thing come to be? The answer is not simple, and the truth is, we are still piecing it together. The formation of supermassive black holes remains one of the deepest mysteries in astrophysics. We know they exist. We have found them at the centers of nearly every large galaxy we have examined, but we do not fully understand how they grow so large. There are several possibilities. Perhaps Sagittarius A began as a stellar mass black hole, the remnant of a massive star that collapsed at the end of its life and grew over billions of years by consuming gas, dust, and stars that wandered too close. Like a snowball rolling down a hill, accumulating mass as it goes. This process is called accretion, and it can be remarkably efficient. As material spirals inward, it forms a disk around the black hole. Friction within the disk heats the material to tremendous temperatures, causing it to radiate energy. But not all of that material escapes. Some of it, perhaps 10%, perhaps more, falls across the event horizon, adding to the black hole's mass. Over billions of years, a seed black hole of a few dozen solar masses could grow to millions of solar masses through steady accretion. But there is a problem with this scenario. We have discovered supermassive black holes in galaxies that are extremely distant, so distant that their light has taken more than 13 billion years to reach us. We are seeing these galaxies as they were when the universe was less than 1 billion years old. And yet, even in that infant universe, these black holes were already massive. Hundreds of millions, even billions of solar masses. They should not have had enough time to grow so large through accretion alone. This suggests that something else must have happened. Another possibility is that supermassive black holes formed directly, without going through a stellar mass stage at all. In the early universe, conditions were very different than they are today. Gas clouds were denser. Gravity was pulling everything together more strongly, and the first generation of stars had not yet polluted the cosmos with heavy elements. Under the right conditions, a massive cloud of primordial gas might have collapsed directly into a black hole, bypassing the star formation process entirely. These so-called direct collapse black holes could have started with masses of tens of thousands, or even hundreds of thousands of solar masses. From there, they would only need modest growth through accretion to reach the millions of solar masses we observe today. A third possibility involves the mergers of black holes. When two galaxies collide, and galaxies collide frequently in the history of the universe, their central black holes eventually spiral toward each other and merge, forming a larger black hole. This process releases tremendous amounts of energy in the form of gravitational waves, ripples in the fabric of space-time itself. Perhaps Sagittarius A* grew through a series of such mergers, each one adding mass and spin to the growing giant. The truth is likely some combination of all these processes. Sagittarius A* probably began as a seed, whether from a massive star or direct collapse, and then grew through both accretion and mergers over billions of years. But growth comes at a cost. As a black hole feeds, it releases energy, tremendous amounts of energy. The material falling inward heats up, glows, produces radiation across the entire electromagnetic spectrum. This radiation pushes back on the surrounding material, potentially blowing it away and starving the black hole of fuel. This creates a kind of feedback loop. The black hole feeds until it becomes so luminous that it pushes away the very material it needs to grow. Then it dims, allowing more material to fall inward, and the cycle repeats. This feedback is not just a curiosity. It has profound effects on the galaxy itself. The energy released by an actively feeding supermassive black hole can heat the gas in the surrounding galaxy, preventing it from cooling and collapsing to form new stars. In this way, the black hole regulates star formation across the entire galaxy. This is why astronomers believe there is a relationship between the mass of a galaxy's central black hole and the properties of the galaxy itself. They grow together, locked in a cosmic dance of mutual influence. Sagittarius A, as we mentioned, is relatively quiet now, but it was not always so. There is evidence, written in the gas clouds and magnetic fields around the galactic center, that Sagittarius A* was much more active in the recent past. Perhaps as recently as a few million years ago, it may have flared brilliantly, consuming a large mass of material and blasting radiation into the surrounding space. We can see hints of this ancient activity in structures called the Fermi bubbles, enormous lobes of hot gas extending thousands of light years above and below the galactic plane. These bubbles may have been inflated by jets of particles launched from Sagittarius A* during a period of intense feeding. Like a dormant volcano, the black hole may have periods of violent activity separated by long periods of quiescence, and it could happen again. In fact, astronomers are currently watching something that might trigger the next feeding event. There is a cloud of gas, designated G2, that has been falling towards Sagittarius A star. Astronomers have tracked this cloud for years, watching it stretch and distort as tidal forces tear it apart. Some predicted that when the cloud reached its closest approach, it would be consumed by the black hole, producing a bright flare of radiation. But when the moment came, in 2014, nothing happened, or rather, nothing dramatic. The cloud passed by, was stretched and heated, but did not produce the fireworks astronomers had hoped for. It turns out that G2 may not have been a simple gas cloud after all, but rather the dusty envelope around a star. The star survived the encounter, and the envelope was only partially stripped away. Still, the encounter is not over. Material from G2 continues to orbit and settle toward the black hole. In the coming decades or centuries, some of it may eventually fall in, producing flares that future astronomers will observe. The region around Sagittarius A* is not empty. It is filled with material, gas, dust, radiation, magnetic fields, all of it caught in the black hole's gravitational grip, all of it slowly, inexorably spiraling inward. There are streamers of gas stretching across the central light year, glowing faintly in infrared and radio wavelengths. There are stellar winds from the massive S-cluster stars, blowing at thousands of kilometers per second, colliding and shocking and heating the surrounding medium. And there's the accretion flow itself, the hot, tenuous gas that is actively falling into Sagittarius A* right now, at this very moment. This accretion flow is puzzling. It does not form a neat, organized disk like astronomers expected. Instead, it seems chaotic, turbulent, with clumps and filaments of hot plasma swirling erratically around the black hole. Part of the reason for this chaos is magnetic fields. Magnetic fields play a crucial role near black holes. They thread through the accretion flow, connecting regions of plasma, channeling energy, launching jets. The interaction between gravity, gas pressure, and magnetic tension creates a complex, dynamic environment. In the image of Sagittarius A* captured by the Event Horizon Telescope, you can see this turbulence. The ring is not smooth. It is lumpy, with bright spots and dim regions, changing on timescales of minutes. This is the magnetic turbulence in action, creating transient structures that flicker and evolve as the plasma orbits the black hole. Some of this plasma may be accelerated to nearly the speed of light by magnetic processes we do not fully understand. These relativistic particles produce synchrotron radiation, radio waves generated by charged particles spiraling around magnetic field lines. This is what the Event Horizon Telescope detected. Radio waves from electrons dancing in magnetic fields just outside the event horizon. There is something almost alive about it, the way the plasma churns and writhes around the black hole. Something organic, pulsing, breathing. Of course, it is not alive. It is governed entirely by physics, gravity, electromagnetism, thermodynamics. And yet, the complexity that emerges from those simple laws is staggering. Chaos and order, intertwined. Let us return, for a moment, to the question of what happens inside the event horizon. We cannot see inside. We cannot send probe to measure conditions there and report back. Once something crosses the event horizon, it is lost to us forever. But we can use mathematics to explore what might happen. According to general relativity, once you cross the event horizon, all paths lead inward. It is not merely that escaping is difficult. It is that outward ceases to be a direction you can move. The geometry of space-time itself has changed so radically that all future directions point toward the singularity. You would have no choice but to fall inward, even if you fired your rockets at full thrust. The singularity is not a place you travel to. It is an event in your future, as inevitable as tomorrow. But how long would it take to reach the singularity after crossing the event horizon? For Sagittarius A*, the answer is surprisingly brief. Only about 10 seconds. 10 seconds from the point of no return to the end of everything you are. Of course, those 10 seconds would be complicated. The tidal forces would grow stronger with every moment. You would be stretched, compressed, torn apart at the molecular level. The very atoms of your body would be pulled into long, thin threads. And time, from your perspective, would continue to flow normally. You would not experience the universe aging rapidly around you, as science fiction sometimes depicts. That time dilation effect works the other way. It is the outside universe that would see you frozen. From your perspective, falling in, the universe outside would appear to speed up. The stars would whirl faster in their orbits. Millions of years might pass outside while you fell for mere seconds, but you would never know it because there would be no way to send information back. The singularity itself remains a mystery wrapped in mathematics. Some physicists speculate that quantum effects might become important at the center of a black hole, preventing the formation of a true singularity. Perhaps there is a region of extremely high but finite density, a Planck star, or a gravastar, or some other exotic object. Others suggest that black holes might be connected to other regions of space-time, wormholes leading to distant parts of the universe, or even to other universes entirely. But these are speculations. Beautiful, intriguing speculations, but speculations nonetheless. The truth is, we do not know. And until we have a complete theory of quantum gravity, we may never know. What we do know is that Sagittarius A asterisk is there. Real, massive, undeniable. It has shaped the evolution of our galaxy. It has flung stars into eccentric orbits and swallowed clouds of gas. It has anchored the Milky Way for billions of years, a silent gravitational heart around which everything turns. And it is still there now, at this very moment, 26,000 light years away, hidden behind veils of dust. It sits in perfect darkness, waiting for the next star to wander too close, waiting for the next cloud of gas to spiral inward, waiting, patient and eternal, as it has waited since before our sun was born. There is a question that haunts astronomers who study Sagittarius A question that lingers in the quiet moments between observations, in the gaps between data points. What would happen if something large fell in? Not a cloud of gas, not a wisp of stellar wind, but something substantial. A star, perhaps, or another black hole. The answer is both spectacular and terrifying. Let us imagine, for a moment, that a star, perhaps one of the S-cluster stars, or a wandering interloper from the bulge, somehow had its orbit perturbed, nudged by a gravitational interaction with another star, sent spiraling inward on a collision course with Sagittarius A. As the star approached, tidal forces would begin to pull at it. The side facing the black hole would feel a stronger gravitational pull than the far side. Slowly at first, then more rapidly, the star would begin to stretch. This stretching would generate heat, tremendous heat. The star's outer layers would be pulled away, streaming toward the black hole in long, glowing filaments. The process is called tidal disruption, and it is one of the most violent events that can happen to a star. The material stripped from the star would not fall directly into the black hole. Conservation of angular momentum would cause it to spiral inward, forming an accretion disk. This disk would heat up due to friction and compression, reaching temperatures of millions of degrees. And it would shine. Oh, how it would shine. For a brief time, perhaps a few months or years, Sagittarius A* will become one of the brightest objects in the galaxy. It would emit X-rays, ultraviolet light, visible light, flooding the galactic center with radiation. The quiet, dormant black hole would awaken, blazing like a beacon. From Earth, we would see this light, though not immediately. The light would have to travel 26,000 years to reach us, passing through clouds of dust that would absorb most of the visible wavelengths. But in X-rays and infrared, we would detect the flare. Our telescopes would record the death cry of a star being consumed by the abyss. This is not a hypothetical scenario. It happens. In other galaxies, astronomers have observed tidal disruption events, stars being torn apart by supermassive black holes. Each event is unique, but they all share certain characteristics. A sudden brightening, a gradual fading over months or years, a spectrum that reveals the chemical composition of the destroyed star. Sagittarius A has almost certainly consumed stars in the past. The S-cluster stars exist in such a chaotic gravitational environment that collisions and close encounters must be common on cosmic timescales. Over the billions of years that the black hole has existed, hundreds or thousands of stars may have met this fate. And it will happen again. Someday. Perhaps in 1,000,000 years. Perhaps tomorrow. A star will wander too close, and Sagittarius A* will feed. But what if something even more dramatic occurred? What if two supermassive black holes collided? This is not mere speculation. We know that galaxies merge, and when they do, their central black holes eventually find each other. The Milky Way itself is on a collision course with the Andromeda Galaxy. In about 4 billion years, the two galaxies will collide, their stars passing through each other like ghosts, their gas clouds colliding and igniting in bursts of star formation. And at the heart of Andromeda is another supermassive black hole, with a mass of perhaps 100 million suns. Eventually, Sagittarius A* and Andromeda's black hole will spiral toward each other, locked in a gravitational embrace. They will orbit each other, closer and closer, radiating energy in the form of gravitational waves. And finally, after millions of years of this deadly dance, they will merge. The merger of two supermassive black holes is one of the most energetic events in the universe. In a fraction of a second, the collision releases more energy than all the stars in the observable universe emit in that same time. Most of this energy is in the form of gravitational waves, ripples in space-time itself, expanding outward at the speed of light. These waves would wash over the remnant galaxy, over any civilizations that might exist at that distant time, carrying the news of the merger. Detectors, if any still exist, would record the signal, a rising chirp as the black holes spiral together, a peak as they merge, and then a ring down as the combined black hole settles into its new, stable configuration. The resulting black hole would be larger than either of its parents, perhaps 105 million solar masses, perhaps more, if the black holes have continued to feed in the intervening billions of years, and it would be spinning rapidly. The merger imparts tremendous angular momentum to the combined black hole, setting it rotating at perhaps a significant fraction of the maximum possible rate. But that is billions of years in the future. For now, Sagittarius A* orbits peacefully through the cosmos, and the Andromeda Galaxy is still 2.5 million light-years away, a faint smudge in our night sky. For now, there is only the waiting. Let us turn our attention to something smaller, but no less fascinating: the photon sphere. The photon sphere is a region around the black hole where gravity is so strong that light can orbit in circular paths. Photons, particles of light, can circle the black hole indefinitely, neither falling in nor escaping. For Sagittarius A*, the photon sphere has a radius of about 18 million kilometers, about 1.5 times the radius of the event horizon. This is an unstable orbit. Any slight perturbation will cause the photon to either spiral inward across the event horizon or escape to infinity. But in theory, if you could place a photon at exactly the right distance, moving at exactly the right angle, it would orbit forever. If you were to hover just outside the photon sphere, held in place by impossibly powerful rockets fighting against the incredible gravitational pull, you would see something extraordinary. Looking outward, you would see the universe compressed into a small circle behind you. The stars, the galaxy, everything squeezed into a shrinking patch of sky. Looking tangent to your position, you would see yourself, your own back. Light from your body would travel around the black hole and return to your eyes. You would see multiple images of yourself receding into the distance, each one fainter than the last as the light made additional orbits. And looking inward, toward the event horizon, you would see the photon sphere itself, a bright ring where light is perpetually trapped, orbiting the black hole in unstable equilibrium. Of course, no material object could hover there. The tidal forces would be immense, and the energy required to maintain your position against the gravitational pull would be astronomical. You would need to accelerate at millions of times Earth's surface gravity, continuously, just to avoid falling in. It is a place that can exist only in mathematics and imagination. But photons can go there, and in the image captured by the Event Horizon Telescope, we are seeing light that has orbited close to the photon sphere, bent and twisted by the black hole's gravity into that bright, glowing ring. There is another peculiar feature of black holes that we must discuss: the ergosphere. Because Sagittarius A* is rotating, spinning on its axis, it drags space-time around with it in a process called frame dragging. Near the event horizon, this effect is so strong that it creates a region where nothing can remain stationary, no matter how hard it tries. This region is called the ergosphere. It exists outside the event horizon, in a shape that bulges outward at the black hole's equator. If you entered the ergosphere, you would be forced to rotate with the black hole. Your rockets could fight against falling inward, but they could not prevent you from being dragged around. Space itself is moving, and you must move with it. But here is the remarkable thing. It is theoretically possible to extract energy from the ergosphere. This process is called the Penrose process, named after physicist Roger Penrose, who discovered it. The idea is to send a particle into the ergosphere and split it into two pieces. One piece falls into the black hole, carrying negative energy. The other piece escapes, carrying more energy than the original particle had. The net result is that you have extracted energy from the black hole's rotation. You have slowed it down ever so slightly and converted that rotational energy into usable form. This is not science fiction. It is permitted by the laws of physics, though whether it is practical is another question entirely. An advanced civilization, far more advanced than ours, might potentially harvest energy from a rotating black hole in this way. They could, in principle, extract up to 29% of the black hole's total mass energy by slowing it down from maximum rotation to zero. For Sagittarius A asterisk, with its mass of 4 million suns, that represents an almost incomprehensible amount of energy, enough to power a galaxy-spanning civilization for billions of years. Of course, we have no evidence that anyone is doing this. Sagittarius A asterisk shows no signs of artificial manipulation, but the possibility exists, written into the fundamental structure of space-time. There are so many possibilities, so many things we might one day do or discover. But for now, we are observers, witnesses to the black hole's existence, students of its nature. And what we have learned is already profound. We have learned that black holes are not merely theoretical curiosities but real objects, woven into the fabric of the universe. We have learned that they govern the evolution of galaxies, regulate star formation, shape the cosmos on the largest scales. We have learned that gravity, that most familiar of forces, the one that keeps our feet on the ground, can become so intense that it warps space, slows time, and traps light itself. We have learned that the universe is stranger, more beautiful, more intricate than we ever imagined. And yet, for all we have learned, there is so much we do not know. We do not know how supermassive black holes first formed. We do not know what lies at the singularity. We do not know if black holes truly evaporate through Hawking radiation, or what happens when they do. We do not know if they connect to other universes, or if information that falls in is truly lost forever. These are questions for future generations, for the astronomers who will build larger telescopes, more sensitive detectors, who will peer deeper into the cosmos and deeper into the nature of space-time itself. But even now, Even with our limited knowledge, we can appreciate what Sagittarius A* represents. It is a monument to the power of gravity, a testament to the universe's capacity for extremes, a reminder that in the heart of our own galaxy, hidden from view but present always, there exists something utterly beyond our everyday experience. 4 million times the mass of our Sun, compressed into a region smaller than our solar system. Invisible, yet undeniable. Silent, yet speaking volumes through the orbits of the stars it commands. Patient, eternal, waiting at the center of everything. As we approach the end of our journey to the galactic center, let us consider what Sagittarius A* means for us, for humanity, for our understanding of our place in the cosmos. We are creatures of a small, rocky world, orbiting an ordinary star in the outer reaches of a spiral arm. We are 26,000 light-years from the galactic center. In cosmic terms, we live in the suburbs, the quiet outskirts, and yet, we are connected to Sagittarius A* in ways both profound and subtle. Every atom in your body was forged in the heart of a star. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of it was created by nuclear fusion in stellar cores, then scattered into space when those stars died. But the orbits of those stars, the paths they took through the galaxy, the regions where they formed and the places where they died, all of that was influenced by the gravitational pull of Sagittarius A star. The black hole does not merely sit at the center of the galaxy. It shapes the galaxy. It determines the density of stars in the bulge, the structure of the bar, the flow of gas through the central regions. It influences when and where stars form, how galaxies merge, how the Milky Way has evolved over billions of years. In this sense, you are connected to the black hole. Your existence is part of a vast tapestry woven by gravity, time, and the slow evolution of galactic structure. There is something humbling about this, something that puts our daily concerns into perspective. We live our lives on a timescale of decades. We worry about tomorrow, next week, next year. But Sagittarius A* operates on timescales of millions and billions of years. It has existed since before our sun was born. It will exist long after our sun has died and become a cold, dark cinder. The stars in the S-cluster, whipping around the black hole at thousands of kilometers per second, complete their orbits in years or decades. But to Sagittarius A*, even these rapid motions are barely perceptible. 100,000 orbits is nothing to an object that has existed for 10 billion years. And yet, despite the vast gulf in timescales, despite the incomprehensible differences in mass and energy and gravitational influence, we have found a way to study it. We have peered across 26,000 light-years of space. We have observed the motions of stars with such precision that we could calculate the mass of an invisible object to within a few percent. We have built a telescope the size of the Earth, and captured an image of the event horizon itself. This is the power of human curiosity, the power of science, the power of patient observation and careful reasoning. The discovery and study of Sagittarius A* represents one of humanity's great achievements. It required decades of work by hundreds of scientists. It required the development of new technologies, adaptive optics, infrared detectors, radio interferometry, supercomputers to process the data. It required international collaboration. The Event Horizon Telescope involved teams from dozens of countries, working together toward a common goal. Political boundaries became irrelevant in the face of a shared desire to understand the universe. And it required patience. Oh, such patience. Andrea Ghez and Reinhard Genzel spent more than 20 years tracking the orbits of stars around Sagittarius A star. 20 years of observations, year after year, slowly accumulating data, watching the stars trace their elliptical paths. In 2020, they were awarded the Nobel Prize in Physics for this work. 20 years of patience, rewarded with one of science's highest honors. But the work is far from over. Even now, astronomers are planning new observations. They want to track the orbits of stars even closer to the black hole than S2. They want to observe variations in the brightness of Sagittarius A* on timescales of minutes, watching the hot plasma swirl around the event horizon in real time. They want to detect the gravitational waves produced when stellar mass black holes or neutron stars spiral into Sagittarius A star. They want to measure the black hole's spin with greater precision. They want to test Einstein's theory of general relativity in even more extreme conditions. They want to understand. And understanding, in the end, is what drives us. Not profit, not power, but simply the desire to know, to comprehend, to peer into the darkness and see what is there. There is a philosophical dimension to all of this that we should not ignore. Black holes force us to confront the limits of knowledge. The event horizon is not merely a physical boundary. It is an informational boundary. It separates the knowable from the unknowable. We can never see what happens inside a black hole. We can never retrieve information that has fallen past the event horizon. There are questions we can ask, rigorously and precisely, that the universe will not answer. This is unsettling. Humans are creatures who seek control, who want to understand everything, to know all secrets. But black holes teach us humility. They remind us that there are limits to what we can know, boundaries to human understanding that cannot be crossed. And yet, even this limitation is itself a kind of knowledge. We understand why we cannot see inside a black hole. We understand the physics that prevents information from escaping. We understand the structure of space-time that creates this barrier. Our ignorance is not merely ignorance. It is informed ignorance. We know what we do not know, and we know why. There is a peculiar satisfaction in that. Let us return, one final time, to the image captured by the Event Horizon Telescope. That blurry orange ring, with its dark center, it is, in many ways, an unremarkable image. You have seen more detailed photographs of planets, nebulae, galaxies. You have seen images of far greater aesthetic beauty. But this image is different. This is a photograph of the edge of a black hole, a boundary where the laws of physics as we know them are stretched to their limit. A place where space and time become so warped that our everyday intuitions completely fail. And we captured it. We, tiny creatures on a tiny world, using our intelligence and our tools and our patience, reached across the galaxy and photographed the unseeable. It makes you wonder what else we might achieve, given time, given dedication, given the will to understand. Perhaps one day, centuries or millennia from now, our descendants will travel to the galactic center. They will observe Sagittarius A asterisk not from 26,000 light years away, but from orbit. They will watch the S-cluster stars in real time, see them whip past the event horizon every few years. Perhaps they will drop probes into the black hole, gathering data up until the moment they cross the event horizon and communication ceases forever. Perhaps they will build structures around the black hole, harvesting energy from its rotation, using it to power a civilization that spans the galaxy. Or perhaps they will simply observe it, as we do now. Watch it, study it, marvel at it. There is no way to know what the future holds, but the fact that we can imagine these possibilities, that we can conceive of a future in which humanity has become something greater, something wiser, something more capable, that itself is a kind of hope. And so we return to where we began. Sagittarius A star, the gravitational anchor, the heart of the Milky Way, 4 million times the mass of our Sun, sitting quietly at the galactic center, invisible to our eyes, but undeniable in its presence, known to us only by the way it makes the stars around it dance. It has been there for billions of years. It will be there for billions more. Stars will continue to orbit it. Gas will continue to spiral inward. The black hole will continue to grow, incrementally, patiently, as it has always done. And we will continue to watch, to measure, to calculate, to wonder, because that is what we do. That is what makes us human. We'll look into the darkness, and we seek to understand. And now, dear traveler, our journey to the center draws to a close. You have descended with me through 26,000 light years of space, through the spiral arms and the molecular clouds, through the golden glow of the ancient bulge, down to the very heart of our galaxy, to the event horizon of a supermassive black hole. You have learned of tidal forces and time dilation, of photon spheres and accretion disks, of stars that orbit at thousands of kilometers per second, and of the patient observations that revealed the invisible giant they orbit. You have stood, in imagination, at the edge of the abyss. You have gazed upon the darkness at the center of everything. Rest now. Let these thoughts settle. Let the vastness of what you have contemplated wash over you like a gentle tide. Sagittarius A asterisk is there, always there, sitting at the center of the galaxy, patient and eternal, a monument to gravity, to time, to the strange and beautiful architecture of the universe. And you are here, a consciousness contemplating the infinite, a small part of the cosmos that has become aware of itself. There is wonder in that. There is meaning. Ancient stars and blue stragglers. You step outside at night, and you look up. The sky takes your breath away. There is no darkness, none at all. The sky is filled with stars, thousands upon thousands of them, bright enough to read by, bright enough to cast multiple overlapping shadows on the ground. The light is golden, warm, like perpetual twilight. The brightest stars are not points of light but tiny disks, close enough that their surfaces are resolved to the naked eye. If you lived there, your night sky would be as bright as 1,000 full moons. You could walk through a forest at midnight and see every leaf on every tree. You could read a book by starlight alone. The temperature would barely drop when your sun set, because the collective heat from thousands of nearby stars would warm the atmosphere, and you would never, ever see true darkness. This is what it is like in the core of our galaxy. In the densest regions of the bulge, stars are packed so tightly together that they are only light weeks apart. Not light years, light weeks. In some places, perhaps only light days. Compare this to our neighborhood. The nearest star to our sun is Proxima Centauri, 4.24 light years away. In the galactic center, that same distance might contain dozens, even hundreds of stars. They are close enough to influence each other, close enough to exchange material, close enough that their fates become intertwined. Let us speak first of the ancient stars. The bulge is old, profoundly old. Most of the stars there formed between 10 and 13 billion years ago, when the universe itself was only a few billion years old. They are population 2 stars, metal poor, primitive, born from gas that had not yet been enriched by multiple generations of stellar death and rebirth. These stars are the elders, the witnesses. They have been shining since before our sun existed, since before the solar system formed, since before the Earth coalesced from the primordial disk of dust and gas. If you could somehow speak to them, they could tell you stories of the early galaxy, when star formation was violent and chaotic, when the Milky Way was still finding its shape. Most of these ancient stars are red giants and orange dwarfs. They are cool stars, with surface temperatures of only a few thousand degrees Kelvin. They burn their fuel slowly, economically, stretching their lifespans across billions upon billions of years. Some of them are K-dwarfs, stars slightly smaller and cooler than our sun. These stars are remarkable for their longevity. A K-dwarf can shine for 20, 30, even 40 billion years, longer than the current age of the universe. A K-dwarf born when the galaxy was young is still only partway through its life. Others are M-dwarfs, red dwarfs, even smaller and cooler. These are the true immortals of the stellar world. The smallest red dwarfs can burn for 1 trillion years or more. Not a single red dwarf has ever died of old age. Not one. They will all still be burning long after stars like our sun have exhausted their fuel and faded to darkness. Imagine that. Imagine a star that will outlive everything, that will still be shining when the last massive star has exploded, when the last white dwarf has cooled to blackness, when the universe is cold and dark and nearly empty save for these patient embers. The red dwarfs of the galactic bulge will be the final witnesses, the last lights to go out. But age brings changes. Many of the ancient stars in the bulge are no longer on the main sequence. They have exhausted the hydrogen in their cores and moved on to later stages of stellar evolution. Some have become red giants, stars that have swollen to enormous size as their cores contract and their outer layers expand. A red giant can be 100 times larger than it was during its youth. If you placed one where our sun is, its surface might extend past the orbit of Earth. These giants are dying, though the process is slow. They are burning helium in their cores now, fusing it into carbon and oxygen. When that fuel is exhausted, they will shed their outer layers into space, creating beautiful planetary nebulae, and the cores will collapse into white dwarfs, dense, hot remnants about the size of Earth but with the mass of the Sun. In the crowded environment of the galactic center, these late stages of stellar evolution create fascinating interactions. When a red giant sheds its outer layers, the material does not simply drift away into empty space. It is captured by the gravitational fields of nearby stars. It swirls around them, sometimes forming accretion disks, sometimes falling directly onto the stellar surface. This transfer of mass can rejuvenate old stars, giving them fresh fuel to burn. It can create systems where one star feeds off its companion, growing younger as the other grows older. And it can create blue stragglers. The blue stragglers. Now we come to one of the great puzzles of stellar astronomy. Blue stragglers are stars that should not exist. Let me explain. When you observe a cluster of stars, whether a globular cluster or a region of the bulge, you can determine roughly when those stars form by looking at their colors and brightnesses. Stars age predictably. Massive blue stars burn hot and bright but die young. Smaller yellow and red stars burn cooler but last much longer. In an old stellar population, all the massive blue stars should be long dead. There should be only the cool, dim stars remaining. The old faithful K-dwarfs and M-dwarfs and the aging red giants. And yet, when astronomers looked closely at old clusters, they found blue stars. Hot, massive, bright blue stars. Stars that appeared young, only a few million or tens of millions of years old, in populations that were billions of years old. These were the blue stragglers, stars that had somehow straggled behind their generation, remaining young while everything around them aged. How? The answer, astronomers eventually discovered, lies in stellar collisions and mass transfer. In the dense core of a globular cluster, or in the crowded regions of the galactic bulge, stars sometimes pass very close to each other, and occasionally, rarely, but occasionally, they collide. A stellar collision is not like two rocks smashing together. Stars are not solid. They are balls of plasma, held together by their own gravity. When two stars collide, they merge. Their outer layers mix, their cores combine, and the result is a single, more massive star. This merged star is hotter and brighter than either of its parents. It appears blue and young, even though it was created from the merger of two ancient stars. A rejuvenated star, a phoenix born from the ashes of its predecessors. But collisions are not the only way to create blue stragglers. Another mechanism involves binary star systems, two stars orbiting each other. Over time, as one star evolves and swells into a red giant, it can transfer mass to its companion. The companion, growing more massive, heats up and brightens. It becomes a blue straggler while its partner withers. This process is called mass transfer, and it is common in close binary systems. The stars are locked in a gravitational dance, exchanging material, altering each other's fates. In the galactic center, where stars are so densely packed, both mechanisms are at play. Collisions happen more frequently than anywhere else in the galaxy, and the tidal forces from Sagittarius A* and the chaotic stellar environment can perturb binary orbits, bringing stars closer together and triggering mass transfer. The result is a population of blue stragglers scattered throughout the bulge. Strange, out-of-place stars shining brightly in a sea of ancient red and orange suns. There is something poignant about blue stragglers, I think. They are survivors, in a sense. They have found a way to remain young in an aging population. They have stolen time, borrowed mass, defied the normal progression of stellar evolution, but they are also anomalies. They do not fit. They are out of sync with their surroundings, burning bright and hot while everything around them cools and dims. And they are temporary. Their borrowed youth will not last forever. Eventually, they too will exhaust their fuel. They will swell into red giants, shed their outer layers, and fade to white dwarfs, just like every other star. But for now, they shine, bright and blue and defiant. Let us consider what it means to live in such an environment. If you were on a planet orbiting a star in the galactic bulge, particularly one in the denser regions, your existence would be profoundly different from ours here on Earth. First, the sky. As we mentioned, your night would be as bright as 1,000 full moons. You would have no concept of darkness as we know it. No true night. The stars would be so bright, so numerous, that your planet would receive measurable heat from them. Your astronomers would have a very different view of the universe. From Earth, We can see perhaps 5,000 stars with the naked eye on a dark, clear night. From the galactic center, you might see hundreds of thousands. The sky would be a tapestry of light, almost too bright to look at directly. But this brightness comes with dangers. Cosmic rays, high-energy particles accelerated to nearly the speed of light by supernova explosions, by pulsars, by the chaotic magnetic fields near Sagittarius A star. In the galactic center, the flux of cosmic rays is much higher than in our neighborhood. These particles can damage DNA, cause mutations, strip away planetary atmospheres. Life on a world near the galactic center would need robust radiation shielding, thick atmospheres, strong magnetic fields, perhaps life forms that have evolved repair mechanisms far more efficient than anything on Earth. And then there are the supernovae. In a region where stars are so densely packed, supernovae happen more frequently. Not in your immediate neighborhood. A supernova within a few light years would be catastrophic, but within a few dozen or 100 light years, they would be relatively common. Every few thousand years, a massive star somewhere nearby would explode. The flash would be brilliant, briefly outshining every other star in the sky. For weeks or months, you would have a second sun, visible even during the day. And then would come the radiation, X-rays, gamma rays, a flood of high-energy particles. Your planet's atmosphere would glow with auroras. The ozone layer, if you had one, would be partially stripped away. Life near the galactic center must be resilient, adaptable, capable of surviving in an environment that is both more energetic and more dangerous than anything we experience here. But perhaps life that would also be more aware, more connected to the cosmos. On Earth, we live in a relatively quiet corner of the galaxy. Stars are distant, faint. We can go days, months, even years without thinking about the universe beyond our planet. But near the galactic center, the universe would be immediate, present, undeniable. Every time you looked up, you would see hundreds of thousands of stars. You would see supernovae in your lifetime. You would watch stars move perceptibly over decades, their proper motions visible to careful observers. You would know, viscerally, that you are part of something vast, something ancient, something churning with energy and change. Let us return to the stars themselves. Among the ancient population of the bulge, there are stars of particular interest to astronomers. Stars that can tell us about the early history of the galaxy. These are the Lyrae variables and the Mira variables, pulsating stars whose brightness changes periodically. Our Lyrae stars are old, metal-poor stars that pulsate with periods of less than a day. They brighten and dim, with clockwork regularity. And crucially, their intrinsic brightness is nearly constant across all our Lyrae stars. If you know their period, you know their luminosity. This makes them excellent distance indicators. By measuring how bright an Lyrae star appears and comparing it to how bright it actually is, you can calculate its distance with reasonable precision. Astronomers use these stars to map the structure of the bulge, to determine its shape and size, to trace its density distribution. And what they have found is fascinating. The bulge is not uniform. It has clumps, streams, overdensities in some regions and voids in others. These structures are the remnants of ancient collisions, smaller galaxies that merged with the Milky Way billions of years ago. Their stars now mixed into the bulge but still retaining some memory of their origins. By studying the chemistry and motions of these ancient stars, astronomers can reconstruct the history of the galaxy. They can see which pieces were added when, which mergers shaped the bulge into its current form. The stars are a library, each one containing information written in its spectrum, in its motion, in its age and composition. Some of the stars in the bulge are among the oldest objects in the universe. There are stars there with ages of 13 billion years, perhaps even older. They were born less than 1 billion years after the Big Bang, when the universe was still young and hot and expanding rapidly. These stars contain almost no heavy elements. Their atmospheres are nearly pure hydrogen and helium, with only trace amounts of carbon, oxygen, iron. They are as close to primordial as stars can be. Studying these ancient stars is like reading the first pages of cosmic history. They tell us about the conditions in the early universe, about the first generation of stars that formed and died before these were born. And they remind us of the incredible age of the cosmos. 13 billion years, a span of time so vast that it is almost meaningless to human minds. And yet, these stars have endured through all of it. They have been shining quietly and patiently for longer than our sun has existed, for longer than our solar system, for longer than the Earth. There is a particular star in the galactic bulge that I want to tell you about. Its designation is SMSSJ160540.18-144323.1, though astronomers often just call it the star with no iron. This star is extraordinary. It is one of the oldest stars ever discovered, with an estimated age of over 13 billion years. And its iron content is so low that it is barely detectable, less than 1/10,000,000th the iron content of our Sun. This suggests that the star formed from gas that had been enriched by only a single supernova. One massive star exploded, scattered its ashes into space, and from those ashes this star formed. It is a second-generation star, barely removed from the first stars that ever existed in the universe. And it is still there, still burning, still shining, a witness to nearly the entire history of the cosmos. If that star could speak, what stories it would tell of the early universe, when galaxies were still forming, of the first supernovae, brilliant and violent, of the slow assembly of the Milky Way from smaller fragments, of the birth and death of billions of other stars. It has seen it all, and it remembers, written in the atoms of its atmosphere, in the slow fusion reactions in its core. Now, let us consider the dynamics of the bulge, the way these ancient stars move. In the disk of the galaxy, where our sun resides, stars orbit in relatively orderly, circular paths. They all move in the same direction, like cars on a highway, at speeds of about 220 kilometers per second. But in the bulge, motion is chaotic. Stars that have highly eccentric orbits. Some plunge toward the galactic center, skim close to Sagittarius A asterisk, and then swing back out into the outer bulge. Others orbit in nearly circular paths. Still others move in elongated ellipses tilted at wild angles to the galactic plane. The velocities are high, hundreds of kilometers per second, and the directions are random. If you could watch the bulge and fast forward, it would look like a swarm of bees, each one buzzing in its own direction, crossing and recrossing each other's paths. And yet, collisions are extraordinarily rare. Space is vast. Even in the densest regions of the bulge, the average distance between stars is measured in light weeks or light months. A star could orbit for billions of years and never come close to hitting another. But close encounters do happen. Gravitational tugs, perturbations, one star's gravity pulling on another, altering its orbit ever so slightly. Over millions and billions of years, these small changes accumulate. Orbits evolve. Stars are flung into different regions of the galaxy or drawn deeper into the bulge. Some are ejected entirely, sent flying out of the galaxy at high speed. Hypervelocity stars, fleeing into intergalactic space. The bulge is a place of constant, subtle transformation. There is a type of star in the bulge that I have not yet mentioned. Horizontal branch stars. These are stars that have finished fusing hydrogen in their cores and have moved on to fusing helium. They occupy a specific position on the Hertzsprung-Russell diagram, a graph that plots stellar temperature against luminosity, forming a horizontal line, hence the name. Horizontal branch stars are bright and relatively hot. They are in a stable phase of their evolution, burning helium steadily in their cores. This phase lasts for about 100 million years, a brief moment in a star's life, but long enough to be common in an old population. In the bulge, there are millions of horizontal branch stars. They contribute significantly to the overall light output of the region, adding to the golden glow that characterizes the galactic center. And then there are the planetary nebulae. When a star like our sun reaches the end of its life, it sheds its outer layers into space. These layers expand outward, glowing in beautiful colors as they are ionized by the hot core left behind. The result is a planetary nebula, a ring or shell or cloud of glowing gas, expanding at tens of kilometers per second, shining for perhaps 10,000 years before fading from view. In the bulge, planetary nebulae are common. Thousands of them, scattered throughout the central regions, each one marking the death of an ancient star. They are transient, ephemeral, but also beautiful, a final flourish before the light goes out. As we near the end of our journey, let us reflect on what we have learned. The galactic center is a place of extremes. Extreme density, extreme gravity, extreme age. The stars there are packed together more tightly than anywhere else in the galaxy. They are older, on average, than stars in the disk. They move faster, burn steadier, endure longer. And among them are the blue stragglers, anomalies, survivors, stars that have cheated time by stealing mass from their companions or merging with other stars. If you lived on a world near the galactic center, your experience of the universe would be profoundly different from ours. Your sky would never be dark. You would see hundreds of thousands of stars, bright enough to cast shadows, bright enough to read by. You would witness supernovae in your lifetime. You would watch stars move perceptibly across the sky over decades and centuries. You would know, with absolute certainty, that you are part of something vast and ancient, that the universe is alive with light and motion and energy, and perhaps you would feel a deeper connection to the cosmos, a deeper understanding of your place within it. Here on Earth, we live in a quiet corner. The stars are distant, faint. We can sometimes forget that we are part of a galaxy, part of a universe. But the stars of the bulge do not have that luxury. They are immersed in the galaxy, surrounded by it, shaped by it, and they endure. For billions of years, they have burned. For billions more, they will continue. Patient, ancient, eternal. Rest now, dear traveler. Let the light of 1,000 suns carry you gently into sleep. Let the ancient stars watch over you, as they have watched over the galaxy since before time had meaning. They are there, always there, burning quietly in the golden heart of the Milky Way. Record 45, ancient stars and blue stragglers. In the core of the galactic bulge, stars are only light weeks apart, packed so densely that a planet that would never know true darkness. The sky would glow with the light of hundreds of thousands of suns, ancient stars, most over 10 billion years old, burning with a patient, golden radiance. Among them are the blue stragglers, young-looking stars in an aging population, rejuvenated by stellar collisions or mass transfer from companions. They are anomalies, phoenixes born from the merger of dying stars. These ancient stars have witnessed nearly the entire history of the cosmos, their light a testament to time itself. Librarians note, if you lived there, your night sky would be as bright as 1,000 full moons. Imagine never knowing darkness, never seeing true night. The stars so close, so numerous, that they warm your world with their collective light. You could read by starlight. You could see your shadow cast 100 times over, from 100 different suns. This is the heart of the galaxy, crowded, luminous, alive with ancient fire. The stars there have been burning since before our sun was born. and they will burn long after it has died. They are the elders, the witnesses, the keepers of deep time. Sleep now, wanderer. The ancient stars keep their vigil, patient and eternal. Let their light embrace you. Let their age comfort you. You are watched over by suns that have seen the birth of galaxies.